Up, we've got integral 0 to 2 pi. Okay, 25 cosine squared t minus 30 cosine t, cosine 5t. And then plus 5 cosine squared 5t dt. And that's it. All right, I'm sorry I have to close class or end class early today, but I appreciate y'all coming, and I'm just messing with you. You doing all right? Yeah. Okay. Just to be fair, I let everyone know my wife told me right before class that she has COVID, so, you know, there's that chance that I have it. So if you want to bail, I understand. Okay, yeah? It's not fun, but it's definitely doable, right? I mean, like this one right here, power reduce, right? Power reduce here. What about this one, though? This one's a little unusual. Anyone know how to handle that one? And we should probably talk about that one, huh? So back in pre-cal, we had these formulas that you don't cover, like, it's like 1 day, 10 minutes maybe, and they're called product to sum formulas, product to sum. Now they're on your formula sheets, okay? They're on your formula sheets, but what I'm going to do is I'm going to do product to sum identities, okay? Let me just bring it up. I'll just grab the first one I see here. Here they are. Can y'all see these? So if you ever have two cosines multiplied, cosine A times cosine B, you can turn it into this. Now, it looks weird, but doesn't it create a sum? And then I can do each one individually? Right. So that's the advantage of these formulas. I think I'm going to want to use this one. So that middle piece right here, let's rewrite what that middle piece is going to be. Let's just do the cosine t, cosine 5t. Let's not worry about the negative 30 in front of it. According to that formula, it would become 1/2, and then cosine of what? A plus b. So those two added, 6t, and then plus cosine 4t. See, and if I do that, then I can do them individually. Oh, yeah, they were backwards up here. Would it matter? I'm just asking, would it matter?
Oh, no.
If I put a negative in there, would it change it?
You could still solve it.
Would it be a different answer? Is cosine even or odd? Like if you plug in cosine of negative pi over 2 is the same as positive pi over 2. Yeah? Cosine. So it didn't, but to follow the formula, it should have been here.
Yeah. Okay.
Yeah. For some reason in my mind, I was thinking it was the other way around. So first we add them, and then we take that one, subtract that one, we get that one. But at the end of the day, this is still just cosine 4t. Okay, I just want to make sure y'all see how I'm going to deal with that middle one, right? That's how I'm going to deal with this one. These two I'm going to do power reducing on. Okay? Let's continue. Any questions? All right, so integral 0 to pi. All right, 25, okay, that's going to turn into 1/2, 1 plus cosine 2t. Okay, minus, now let's distribute a negative 30 through this, right? So that becomes negative 15. Negative 15 cosine 6t, and then I have plus, but it was a minus, right? So minus 15 again, cosine negative 4t, and then plus 5 times 1/2, and then 1, and then plus cosine, and then 2 times the argument. So what? 10t, right there, dt. Okay. Power reducing, right? Product to sum, distributing the negative 30 through. And then 5, and then power reducing or half angle. Is that clear? Okay. And then now I need to do these. All right, this is 25 over 2. Okay, that's just this. And now I'm going to do antiderivative of those separately. So t plus a half sine 2t. That's the antiderivative of this, right? Okay, let's see. For this one, minus 15 over 6, because I'm doing the antiderivative of that would be 1/6 sine 6t. So 15 over 6 sine 6t. And then for this one, the antiderivative of that, if I keep the negative here, which I will, I'll get negative 1/4 out front, sine negative 4t. So that'll become a positive 15 over 4 sine of negative 4t. And then, let's see, plus 5 over 2, and then antiderivative each of those, so t plus 1/10 cosine 10t, cosine sine of 10t, all of that, right? All from 0 to 2 pi. Now let me ask you something here. When I start plugging in these things, 2 pi and 0, aren't those, in terms of signing, well, all we have is sines in here, right?
Yeah.
Sine of 2 pi and sine of 0 give you the same value, don't they?
Yeah.
So when I plug 2 pi into here, that's 4 pi, 0, right? 2 pi into here, it's 12 pi, 0, 0. So we're really having, nothing is, the 2 pi and the 0, we're getting no contribution from the sine pieces, are we?
Yeah.
Even if we did that, they would cancel each other out,
Yeah.
right? Okay?
Yeah,
You sure?
yeah, just in the beginning we said we let out x and 0. If that changed our answer, if we let y and 0.
If we let, oh, would it, oh, you're asking if we would have done, yes, we would have a different integral in here.
Yeah.
Yeah, it wouldn't change this, but it would change what's in here. The integram would be different. Okay, so let's go 2 pi into the, let me, I'm just going to not even look at the parts that have sine in them, because I know those are going to go away, right? So let's plug in 2 pi right now for t. So we should get 25 over 2, right, times, this is just going to be 2 pi. Nothing here, over there, right there. So plus 5 halves times 2 pi, right? That's what I get when I plug in 2 pi. And then when I plug in 0, it all goes away. So this should be my answer. The 2's cancel here. I get 25 pi. 2's cancel there, I get 5 pi. So 30 pi. 30 pi is the area of that region. Okay? Now, do y'all want to try it using a different P and Q?
To be honest, this looks like either way it would have been complicated.
Yeah, I mean, it's not going to be better. You're still going to have sines or cosines in there. Oh, I did it on the computer. 30 pi. Makes it feel better that we got it, right? We got the same thing? Okay. All right, let me erase this and we're going to move on to the next example. That was worth it just so we could remember that we have the product to sum formula, right? For that cosine, cosine next to each other. All right. I think we did a problem like this back in, I don't even remember. Okay, find the line integral over C of f dr. I want to know the work, right? Work, right? That's work. If you're trying to move along this triangle from 0, 0 to 2, 6 to 2, 0, back to 0, 0, and you're trying to move through this vector field. Okay, so I give you a field, right? I give you a curve to path to traverse, right? Let's start by just drawing C first, all right? So let's go with C here. My picture is, I start at 0, 0, right? This is where I start. I then go to where? Up 2 and over 6. Right there. Wait, hold on. To here, sorry. To there, not this point. So I go from here to here. And then down to 2, 0. Or 2, 6. Wait, what the hell? 2, 6 to 2, 0. Whoa, I'm totally messing myself up here. I got to read what's up there. Not going down. Where am I going? Here, right? Wait a minute. What the? 0, 0 to 2, 6 to where? 2, 0 to 0. I think that's a typo.
No, it's just, but you have the x-axis on the y.
Oh, fuck. Have I told you about math purgatory yet? No? Did I mention that?
I vaguely remember.
Yeah, so I have this, I don't really believe this, but I kind of do. Y'all have heard of purgatory, right? Like when you die, it's like this like intermediate place that you could go to. Certain religions believe that, right? I believe there's this, like, for me, there's going to be this like math purgatory, where there's going to be all these mathematician gods in there, and they're going to be like playing back all the mistakes I made in lectures, be like giving me lashes. Remember when you plotted 2, 6 is 6, right? I just need to reset, man. 0, 0 is here, right? Where is 2, 6, Robert? 1, 2, 1, 2, 3, 4, 5, 6. There we go. I'm so sorry. Please. Okay, that's 2, 6. 2, 0 is here, right? And back to 0, 0. So we're going from here to here, back down to here, and then back over here. All right, there we go. Please stop. Are we okay with that C? Yes. That's C. So we want the work if we travel along that curve and we're given our vector field. So there's another way I could write this work integral. And this is what I started class with. I said that can be rewritten as the line integral over C of P dx plus Q dy, right? I said that by showing you the notes from the other day, that one right there, right? So I know that I can rewrite that way, where P here would be this, right? That's P. And this right here would be Q. All right? Big deal, right? Big deal. What now? And we're not in an area, huh? Right? We're not trying to find the area of anything. So you know how we used that special case just a second ago?
Yeah.
To find the area of a circle and the area of that epicycloid? That is only when we're trying to find the area of some region D.
Okay.
And then we can use that special case. But here, I'm trying to calculate the work, right? Yeah. I want us to appreciate for a second what this really means, right? This really means that we're going to do this integral. We have to take the field F, right? That's our F field, which is P, Q, and dot that with dr, right? Which is another vector, dt. This will be our limits. But we have to find, we would have to find the path, right? We'd have to find this. So the only way to do that would be to break it up into 3 paths. Line segment, line segment, line segment, right? We don't want to do 3 line segments, do we? But that's what we would have to do if we didn't have Green's theorem. Green's theorem is applicable here because C encloses a region, doesn't it? C encloses a region. Now, I have to pay attention to something here. I'm traversing this with negative orientation. It's clockwise, right? So whatever my answer is, I need to remember to change the sign at the end because I'm going reverse direction. All right? So let's use Green's theorem, right? So because I recognize here that C is closed, right? It's closed. Could have said that in the beginning, but I'm really stressing that to myself. And the orientation is clockwise, right? Clockwise. That this should be equal to the double integral over d. Now, I left a space here because I'm going to go ahead and account for the negative now. Because I'm traversing clockwise. This formula only works when it's counterclockwise unless you change a sign. And then it's the what? Partial, I erased it over there. It was the partial q with respect to x minus partial p with respect to y dA, right? So for us, what is the, let me write it. Partial q with respect to x minus partial p with respect to y dA. By the way, you could pass this through and then switch the order, right? I'm not going to, but you could. Minus double integral over d. Okay, partial of q with respect to x. It's not great, but it's not horrible either. What is it? Partial q with respect to x. 2x plus
2y cosine x.
2y cosine x. Right? That is the partial of this with respect to x. 2x, and then 2y is a constant derivative, that's cosine x. Okay, that. And then I'm going to write this on the line below. Is that all right with y'all? I'm going to do it down here. So this was negative double integral over d. Okay, it was 2x plus 2y cosine x minus, and now the partial p with respect to y. Really? What is it? 2y cosine x dA. Isn't that nice? So this is just the double integral over d of 2x dA. Now, unfortunately, this isn't just 2. If this was just 2, wouldn't it just be, like, bring the 2 out and it would just be the area of the triangle? It's not, though. It's 2x. You can't bring the x out. So this is not as simple as just turning into an area. But can we do this double integral? Can you take the double integral of 2x dA over that d region? So now we are back to when we first were doing double integrals. Look at this region over here. What type region is this? Type 1. This is a type 1 double integral. Okay, give me my restrictions. This is type 1. X restriction is 0 to 2. My y restriction is 0 to whatever this function is, right? How do you find this function? You just need the slope of that line. Slope is 6 over 2, so 3. So y equals 3x is this function right here. Y equals 3x. And I can say 3x because it goes through the origin, right? So the y-intercept out here plus 0, right? So this goes from 0 to 3x. See? So now this becomes, let's see, did I lose my negative? I did. I lost it. It was right here. I lost it. Another one. Right, the negative right here. All right, so here's where we are. We have negative double integral. First one's going to go from 0 to 2. Second one's going to go from 0 to 3x. The order matters, right, because it's type 1. What am I integrating? 2x with respect to y first, then x. See, nothing crazy. It's just a regular double integral now. negative integral 0 to 2. Okay, let's do the inner integral first. Antiderivative of 2x with respect to y. 2xy. Evaluating that from y equals 0 to y equals 3x. And then once I'm done with that, I'll do that with respect to x. Plug in 3x. So minus double, or not double integral, 0 to 2. You get 6x squared, yeah? Is that what you said? And when you plug in 0, you get 0. And so just that. Now we're back in Cal 2. This is 2x cubed evaluated from 0 to 2. We know it's x, right? But I'm just going to put it. And the negative, thank you. And so our answer is negative. Let's see, plug 2 in. 2 cubed 8, negative 16. Plug in 0, you get 0. Negative 16. Negative 16. That sure is better than having to have done our C as 3 separate line segments, finding the parametric equation for each line segment, and then calculating that f dot dr for each one of those. Try it yourself. You can compare the work. Go take an hour to go do that other problem the other way, right? And then you can appreciate this. Nice? Has to be a closed curve. So the negative orientation of the curve here wasn't a big deal, was it? We just made it negative. We solved the problem, so. What if I change the problem and I only asked you to go from 0, 0 to 2, 6? Could you use Green's? If I said, find this where C is just the line segment from here to here, could you use Green's theorem?
No.
No. You have to have, your curve has to enclose a solid, because if you're going to do a double integral, you have to have a region, not a solid, a region. You have to have a region. If it's a line segment, there's no region, right? All right, so this problem, we could live without this next thing I'm about to show you. We could live without it, but it's in the book, and it's one of those times in math where you're going to be asked a question. It seems like there might be absolutely no way to ever solve or answer the question, but there is a way, all right? So that's why I like to go through this. So first, we want to consider D, this region D, which is the one like shaded there. And notice that that D has a hole in it, right? Up to this point, the regions I've been talking about don't have holes in them. In fact, for this region, you wouldn't have a single curve that encloses the region. But you could talk about having 2 curves, right, that enclose that region. So you'd have C1, which would go positive orientation, right? Now, look at C2. Right? It's the other way, clockwise, right? And if you're walking on C2, right? If you're walking on C2, your D is to your left, right? All right, so we have C1, C2. So the question is, can we use Green's theorem for something like this? If we have a hole, right? If we have a hole, can we still use Green's theorem? So let's see if we can reason out whether or not we can. So first thing we want to do is we want to take that. So we had D there, which is this shape here. C2 goes clockwise, C1 goes counterclockwise. We're going to split D into 2 regions, D1 and D2. D1 is now the top half, D2 is this bottom half, right? We still have C1 going around and C2. Is that okay with you? Right, so we split it up. Now what I'm going to do is I'm going to create 2 new paths. 2 new paths. The first path, E1, is the one in yellow here. It's going to go counterclockwise, and it's going to go around D1. Do you see it like that? And then I'm going to create another path, E2. Sorry, it's hard to read this. E2. It's also going counterclockwise, but it's going to go around D2, just D2, right? See those together? So we have E1 and E2. I want you to notice now that when we look at this, right, there's a part, if I were to put those two together, on this little segment and this little segment, do you see that our two paths are going to be traveling in opposite directions? So from here to here is opposite. So when I'm on E1, I go from left to right here, and when I'm on E2, I go from right to left on that segment. Which means that if we add those together as line integrals, they should what? Cancel, because they're in opposite directions, aren't they? And same with this one here. It's left to right here, but from here it's right to left. Right? So they cancel each other out, opposite directions. Therefore, if we want to do Green's theorem, right, double integral over D, back up to the top, double integral over D, what we can do is we can do the double integral over D1 and D2, because we should be able to split it into two separate regions, right? Two separate regions. But then that should just be the line integral over C1 plus the line integral over C2. What was C? C1 was this one plus C2. Because what is C1 plus C2? It's the same as E1 plus E2. Right? E1 was this, E2. You put those together, that's the same as C1 and C2. These parts here don't have to be accounted for because they cancel each other out. This is just kind of to show you that it's okay to just do C1 and C2 added together. You don't need to worry about this piece in here. So that's our result, okay? Recap. If D has a hole in it, you break it up into two regions, which winds up just being the line integral over the two curves. C1, remember, went what direction? C1 went counterclockwise, and C2 went clockwise. That's important because in order for these to cancel out, we had to have that. Okay? I'll say it one more time. If we ever want to do a double integral over D, right, so use Green's theorem, then we can do the line integrals over C1 and C2 respectively, where C1 is the outer counterclockwise path and C2 is the inner clockwise path. Yep? Okay, yes?
So if they're both going like clockwise, they're both going...
If they were both going clockwise, then we couldn't use it unless we reverse the direction of one of them, which we can do by just changing a negative sign out front, right? So like let's say C2 went counterclockwise. Let's say it did. Then this formula would change to a minus. Okay? Because C2 goes the opposite direction for this to work, so we just put a minus here and it would work. Okay? Good. No, it's good. Very good question. So in fact, we're about to use it. Your question I'm going to use in just a second. So here's that problem I'm talking about. Show, what's that integral? Work. Show the work over curve C. Okay? Show the work over the curve C through this vector field is always equal to 2 pi. Or sorry, is equal to 2 pi. Where C is what? Any closed path that contains the origin. What's problematic with something like that? Yeah, how many paths can you come up with that are closed that contain the origin? Infinitely many. So how do you check them? Like you could find one path, right, that encloses the origin, and you could show me that the answer is 2 pi, and I would be like, great, now show it for every path, right? You have to show it for any path that I do. So do y'all know what it means to enclose the origin? It's saying the origin is here, right? Draw me any path that you want, that as long as the origin is inside that path. So, you know, that would be an example of a C. That is a path that encloses the origin, right? But there's an infinite number of paths you could choose. So we need to somehow show the answer is always going to be 2 pi no matter what path we ever choose. Do you see what I'm saying? Like this seems not possible to answer because you can't check every path. All right? Okay. Now, just to rule this out, if this is the origin, if I draw a path that crosses through, do we say that that contains the origin? Do you think that this means that we've enclosed the origin if the origin is actually on the boundary of the curve? No. By definition, enclosed means that the origin has to be inside, not on the boundary. Okay, I just want to make sure we rule that out. Okay, so how am I going to go about this? Look, when you see me do this, it's not going to seem natural. Like you're going to be like, yeah, I never would have thought of that, you know. But that's the whole point of this, is trying to show you how mathematicians can do something like this and give you a general answer without actually ever having to try every path. So here's what we're going to do. I'm going to draw a path, right? An arbitrary path. It's going to enclose the origin. Okay? And y'all just let me know if you're satisfied with that path. Is that okay with you? Is that okay? Is that sufficient for an arbitrary C? I'm going to call it C. And for this C, I'm just going to orient it positively, like that. Now what I need to show you is that the answer to this is 2 pi, right? When I do that, and that's my field. Remember, this would be my P and this would be my Q. Can I use Green's theorem? Yes, I can, right? You could change this to the double integral over D. But there's a problem. What's D? What's D? It's arbitrary, isn't it? It's arbitrary. This could be a triangle. This could be a circle. This could be this shape that you see right here. It could be an epicycloid. All these different things, right? So there's no way I'm ever going to be able to define D to do that double integral, right? So how do I do this? Well, I'm going to use what we just talked about when you have a region that has a hole in it. I'm going to draw a second path, okay? A second path. Now, when I draw this second path, I need you all to kind of like be on board with me here. That if the origin is contained within this curve, do you all agree that there is some circle I can draw? There's some circle. It might have a really tiny radius, but there's some circle I can draw in there that will fit inside your curve and still contain the origin. So if there's going to be on this curve, there's going to be a point that's closest to the origin, right? Like maybe it's about right there. That looks like maybe the point that's closest to the origin. I should always be able to pick a circle with the smaller radius and just draw it in there. Do you all buy that? Okay, so I'm going to say here, I'm going to use, for the radius, I'm going to choose A. Choose A. Let me do it this way. Choose circle with radius A such that x squared plus y squared equals a squared is inside